All right, I'd like to introduce our last presenter, the guy keeping us from lunch right now. So we won't hold that against him. This is Stephen Ball from John A. Martin Associates in LA, and this is their LAX terminal expansion project.
Well, hi, my name is Stephen Ball, and it is with great pleasure that I have the opportunity to present the Tom Bradley International Terminal Project to you on behalf of the design team at John A. Martin out of Los Angeles. The project entails adding a new terminal building and concourses immediately adjacent the existing Tom Bradley International Terminal. But before getting into detail, I'd like to start by giving you a general overview of the LAX campus. The LAX Airport is located in Los Angeles, California, and here you can see the roadway system that services 8 domestic terminals as well as the Tom Bradley International Terminal. The Tom Bradley International Terminal was built in 1984 in preparation for the '84 Olympics that were held in Los Angeles. And as you can see from this photo, it's got 1984 type architecture. The building is outdated, both visually as well as functionally. So the plan was to add a new terminal building and new concourses immediately adjacent the existing terminal, but maintaining the existing terminal in operation for ticketing and administrative use. The new terminal is about 500,000 square feet, and it houses functions such as Customs and Border Protection, FIS, bag claim, concessions retail, and premier lounge space. It anchors about another 500,000 square feet of new terminal space. Once completed, it will provide 15 gates that can accommodate the Airbus A380 or the Boeing B787 Dreamliner super jumbo jets. Altogether, it's going to add about over 1 million square feet of space that's going to eclipse the existing facility, both in size and in appearance. And also, once completed, the existing concourses that are attached to this existing terminal will be removed, but again, this existing terminal will remain. The project is located immediately adjacent to the ocean, which inspired the architectural feature of these sloping curved roofs, which mimic the rhythmic waves of the ocean. And it was this particular geometry that created quite a few structural challenges, which I'll get into during this presentation. So this LEED Silver project is the largest public works project in the city's history. And it's the first major capital improvement project in LAX since 1984 and has a construction cost exceeding $2 billion. Here are some images of the concourses. Here you can see the sloping curved roofs, and each one of these repetitive modules is 125 foot long and over 100 foot in width. Here at these roof transitions, you can see this clear story feature. And it's at this location where we framed it with a Verandil truss spanning 125 feet that is both sloped and rotated about its longitudinal axis, all of which exceeded the conventional limitations associated with the Verandil truss. Here's a view from the opposite side. Again, you can see the sloping curved roofs, and here at the roof transitions, you can see this clear story feature, and it's at this location where we introduced a very unique structural system, which I'll get into. Here's an image inside the concourse. As you can see, it's a very light, bright, voluminous space, relatively column-free. Here's the departures level. Here's the arrivals level. That's also referred to as the sterile corridor. Incoming international passengers enter this sterile corridor, and they stay within this system until they reach customs. The height from here to here is about 65 feet. The overall width is over 100 feet. Here's the Verandil truss that I mentioned earlier that is sloped and rotated about its axes. And here at the crescent clear story, you can see a sloping column, and you see these curved beams. All this geometry was pretty challenging, not only just from the design of the gravity systems, but also in the selection and design of the lateral resisting systems. And it was because of the open character of this architecture, it made the selection of the lateral resisting systems very difficult. We couldn't pursue conventional solutions such as shear walls or diagonal bracing. And so it was at this point that we introduced a pretty bold structural idea of using a non-orthogonal curved moment frames at these crescent clear stories. And that idea raised a lot of eyebrows, mainly because the code does not allow the use of non-orthogonal moment frames in the United States in high seismic regions. And it's not orthogonal in the sense that the angle between the beam and the column is at an angle other than 90 degrees. So not only does the code not allow that, it especially doesn't allow it whenever you have curved beams and sloping columns. But we were convinced that we could prove the viability of the system and that we could ultimately gain approval for use in Los Angeles. Here's a view inside the terminal building. As you can see, it's very similar in character as the concourses, only much larger. The clearance from here to here is 120 feet. The overall width exceeds 200 feet. And here in the background, you can see the concourses, so it gives you a nice contrast in size between the concourses and the terminal building. The structural systems inside the terminal building are very similar to those in the concourse, only much larger, as you can imagine. So we were faced with quite a few design challenges, mainly in the form of complex and unique geometry, high loading, and of course the non-orthogonal moment frames that we had selected, which we had to pursue approval to use. And that I'll get into next. Here's a schematic showing the curved moment frame that we used at the crescent clear stories. Here you can see the sloped column, you can see the curved beams, here's a straight column, and all four of these connections are non-orthogonal. Similarly, in the longitudinal direction, we had sloped beams that were non-orthogonally connected to the columns. And here's a diagrammatic showing the relative placement of the moment frames. Here are the curved moment frames at the crescent clear stories that are spaced at 125 foot centers. And here are the longitudinal moment frames along each side of the concourse. So at this point, we had our structural concepts in place. So we had to figure out, well, how are we going to document this? And it became abundantly apparent that using conventional 2D CAD techniques was not going to be adequate. Because the geometry was complex, we have overlapping surfaces, and so the design team got together and we all collectively decided that the best approach would be to do 3D BIM modeling. So all the respective disciplines, mechanical, electrical, plumbing, fire protection, structural, architectural, civil, we all prepared our own respective BIM models, and they were all integrated into one master model for overall coordination and clash detection. And ultimately, the structural model was incorporated into the BIM model that was created by the steel fabricator to assist in the detailing of his structural steel. And here's an image of the BIM model, structural BIM model for the concourses. We had the roof surfaces turned off so that you can see the structural frame. So now, with the documentation in place, now it was time to face the structural engineering challenges. So it was at this point that we turned to Bentley and their suite of products. And we decided to use RAM structural systems for the design of composite framing, as well as design of the non-composite roof framing, for design of steel columns, for tracking column loads, for designing foundations. And we also use some of the specialty features such as designing the web openings in steel beams and for investigating the vibrational response due to walking loads, and also for the RAM connection module. We use Bentley STAD Pro as well as CSI SAP 2000 for the analysis and design of the complex framing and for performing our lateral three-dimensional dynamic analyses. We had some areas that had two-way slabs that were supporting mechanical equipment. And because it was in a mechanical area, there were quite a few perforations through the slab. Because of the loading and the spans and the geometry, all that exceeded the limitations associated with the equivalent frame method that is endorsed by ACI 318. So we turned to Bentley's RAM Concept. RAM Concept is the RAM steel equivalent for concrete construction. It's a very powerful program. And it took what would have otherwise been a very difficult design task and quite frankly made it very simple and trivial. It's a very powerful program. Here's an image of the RAM Structural Systems model for the terminal building. As you can see, we had no difficulty modeling unusual geometry. Here we have slab edges that are curved and planned. We have sloped framing. We have columns being transferred out on beams. We have different areas with composite construction, different areas with non-composite construction. We got concrete walls. And it is just an invaluable tool to enable us to design such a large project within the time constraints that we were faced with and still provide us the reliability and the accuracy that we needed. But quite frankly, the greatest power that came out of it was its adaptability to change. The airport authority implemented quite a few scope changes during the design and construction of the project, anywhere from adding heavy media features to escalators, elevators, moving things, even adding a whole new floor level to the terminal building after the project was in construction. And we found that we could quickly adapt to those changes and evaluate all the trickle-on effects using RAM structural systems in a quick and efficient manner. Here's an image of the concourses using RAM structural systems. Here you can see the departures level. Here's the arrivals level. This here are the moving walkways that are in departures level. And at the arrivals level, we had some design challenges because the spans were large. Many of those spans were approaching about 100 feet in length. And we were concerned because the incoming passengers enter onto this corridor, and they walk anywhere from 500 to 1,000 feet before they arrive at customs. And we were concerned that people in that type of environment might get into some type of rhythmic motion, which would amplify any structural vibrations. But we were able to use the tools that Bentley provided, mainly in the form of STAD Pro as well as the RAM structural systems, and it provided us the tools that we needed to adequately address or to evaluate the vibrational characteristics of the framing and to proportion the framing to mitigate any vibrations due to the walking loads. And I'm pleased to tell you this is all constructed and has been well tested, and it performs very well and as anticipated. Here's a view of our 3D and dynamic analysis model. We modeled all the columns and the beams. We also modeled the flexibility of the roof diaphragms as well as the flexibility of the concrete diaphragms. And so at this point, we had our structural design and analysis strategies in place, but we still had one major challenge ahead of us, and that was getting the non-orthogonal moment frames approved for use. So we started by performing a nonlinear 3D solid analysis of a typical beam column joint. And this is a model with 300,000 nodes using 20 node hexahedrals and 10 node tetrahedrals, considering cyclic loading. And from the analysis, it showed that the joint would perform adequately. But quite frankly, that's just not good enough for the building officials doing this type of analytical investigation because the code's very explicit. You are now not allowed to use non-orthogonal moment frames in high seismic regions. So they forced us to do full-scale cyclic load testing of the moment frames. We ended up having to do 2 specimens for the curved moment frames as well as 2 specimens for the longitudinal frames. And we performed the cyclic testing in accordance with the provisions of AISC 341, Appendix S. Here's a schematic showing the specimen setup for the curved moment frame. Here you can see the curved beam, and here's the column, here's the load actuator. Similarly for the longitudinal frame, here's the column and here are the beams. And this specimen was also unique in another fashion, is all the prior testing that has been performed that forms the basis of the code uses L-shaped specimens where you have a column with a beam just coming off on one side. This was the first time that a test had been performed in a T-shaped fashion where you have a column and a beam coming off on both sides. This testing was performed down at the University of California in San Diego with the assistance of Dr. Chai-Ming Wong. Here's a photo showing the specimen for the curved moment frame. And you can see from the people in the background, it gives you an appreciation for the size of the specimen. And we're very excited about the results because we tested all 4 specimens. All the results came in favorable. Here you can see, here's a representative hysteresis loop for the beams, showing the classic nonlinear behavior for beams. And then here it shows the elastic behavior of the columns, all of which was anticipated because they were proportioned for the columns to remain elastic and for the beams to have the plasticity in them. And we were able to take these results and go to the building officials and prove the viability of our system. And for the first time ever, we were granted permission to be able to construct these non-orthogonal moment frames. So we broke ground during February of 2010. The first gate was opened during September of this year, and the facility will be in full operation by this coming May. Here's some actual photos during construction. Here's the North Concourse. It's about 500 feet long, and it has provisions to be able to expand it another 500 feet to the north at some future date. Here's the South Concourse. It's about 1,000 foot long. And then here's the Central Terminal building. This altogether, it's almost 18,000 tons of structural steel. And if I had time, I could tell you about another project just prior to this that used 35,000 tons of steel. And it was also used the Bentley products. So needless to say, we've been able to put the Bentley products through some rigorous tests, and it's stood up to the challenges in all cases. I lost my connection. Here's a closer view. Here you can see here are the concourses. Here's the Central Terminal building. Here's a view inside the terminal building. Here's a view inside the concourse. Here you can see the Verandale truss that I described earlier. Here's the crescent clerestory of the slope column and the curved moment frame beams. And here's the departures level, and here's the arrivals level. And here's a photo that was taken at night for the first gate that was opened during September of this year. And this gate's been used, is actually open and is fully operational and has been successful. So in conclusion, we found that the Bentley products could stand up to all the unique challenges that we could throw in its direction. And we also hope that this project goes to demonstrate that structural systems can deviate from customary practice and defy conventional wisdom, and yet still be successfully designed and constructed. All you need to do is just be persistent and be inspired. And with that, I will turn the floor over to any questions you might have.
Thank you, Stephen. Who has the first question?
It was a really nice presentation. I was just curious, does any of the non-linear roof structure have to tie into the existing facility? And if so, how did you do that?
No, there's seismic separation between the new facility and the existing facility, but there are a lot of other complications which I didn't get into in the presentation. In that we at all times we have to maintain full operations of the facility. We cannot disrupt anything. And so there's a lot of phasing issues that go on during construction and during the commissioning of the new facility and phased decommissioning of the existing facility. But the structures are not assisting each other. Yes.
This is a great presentation. I had 2 questions. For the non-orthogonal moment frames, how did you fabricate the connections? Were they welded or were they bolted?
Yeah, they were welded. We used the RBS moment connections that are from ACI 358, but of course we had to adapt it and sort of create our own criteria that would be applicable to the curved nature of the beams and the non-orthogonal nature of the beams.
I see. And the second one, you said you did a coordination into like a master BIM model from the HVAC, the MEP guys, structural and stuff. What was your data format to move your model into that master BIM model?
The architects actually drove that particular model, so I can't speak knowledgeably of all the specifics of it. But I can tell you from seeing what the end product was, it was extremely helpful, especially with the MEP systems, because that's where we detected a lot of clashes with ductwork and pipe. And of course, then it becomes a negotiation, you know, who moves and what gets reproportioned. But it was an invaluable tool.
Thank you.
Any more questions here in the back? All right, well, thank you, everybody, for attending. Question? Felix?
Yeah, having demonstrated empirically that these non-orthogonal moment connections worked, did you get any indication that maybe the authorities would be open to digital demonstrations or models or calculations in the future?
They won't be, because the code is too explicit in that regard. But having said that, Dr. Chai-Ming Wong at the University of California in San Diego, he and I are on a special mission to do additional testing. We've solicited some assistance from different steel fabricators on providing materials and so on, and we're going to do our own testing and see what we can do to inspire AISC to adopt non-orthogonal configurations in future code generations.
All right, any last questions? All right, I won't keep you. Thank you again, Stephen.